Thank you very much. Yeah, great. So, what is Altar? Good question. We're just kicking it off right now, so this is all pretty new. But ultimately, my research career so far, last 15 years, working in soil carbon, soil nitrogen across both the ag and the environmental space. And so I sit in these two worlds, one in agriculture and one in the environmental space. And I sit there in the agriculture stuff and we go to these sort of forums. Sorry, I'll stop moving around. And I look at the tools, and then I go to the ecology space, and it's like, wow, this stuff is amazing. Why aren't we using this in agriculture? Why aren't we using this on our farms? And there's this gap between these two worlds, I suppose, is what Altar is trying to bridge. So what is Altar? It's the Australian Long-Term Agro-Ecosystem Research Network. So a bit of a mouthful, but to be honest, we stole that LTAR idea from the US, which is long-term agricultural research, and we put an A in front of it to make it Altar. But ultimately, you know, we want to build this bridge between these two worlds. That world being this network called Turn, and everything we've been talking about here today. This is a bit of a scary diagram. I'm not going to go in, I'm not brave enough to really go in between the pros and cons of both, but all I want to say is, on this side, this carbon offset world, I'm sure you're all familiar with the controversy around some of the carbon offsets, whether it's around HIR, human-induced regeneration, or soil carbon, and the ACCUs that are generated. Now, what I want to get across today is that those methods have been under development for over a decade. There's been hundreds of millions of dollars spent on developing them, and we're still in this case where we have science battling the industry to the detriment of agriculture. So what happens then in 5 years' time in this space when the regulated market, we're now in the unregulated market? And you know, what lessons can we learn from the rigmarole that has been the carbon offset market, and what can we basically do now to stop the same thing happening in the inset market? Because in 5 years' time, if we don't get the guardrails right now, we might be in the same place. And just to bring it back to the carbon, so great presentation about the trees and the potential that trees have in this world. But what about soil carbon? So soil carbon's a bit more tricky. You can't see the carbon so easy. And it's also very hard to measure. And a lot of the issues with it is just because of that. It's very hard to measure. It's very hard to know if it's actually staying in the ground where it's supposed to. So we wrapped up a CN30 project with all our partners down here, some of which are in the room, looking at a couple of things around, well, can we actually sequester carbon to start with? Now, a bit of a caveat here, we went to the most likely places to actually be able to detect this. So really suitable soils, we're talking about high clay soils, pretty good rainfall, and the Brigalow belt, so pretty good production systems. But what we did find is, yes, looking at the two main avenues, perennial legumes, so in this case it was Desmanthus with Agrimix, we could actually see carbon sequestration. That's great. That's, if you can see it, that's a root down at 1 metre. So there's a mechanism that we can put behind that as well. So it's not just fairy dust. Actually, we can actually explain that scientifically. Look, we can actually see, we're seeing this carbon increase at depth, and we can attribute it to a mechanism. So that's great. The other one we looked at was grazing management. So we're looking at the time control grazing, but across the spectrum of basically controls. And same sort of thing, we saw an impact. I should say these are over paired sites, and this is over 20 years. So we're actually looking at that difference over 20 years. And so over 20 years, yes, we can see those things. So, that's encouraging. There is potential in soil carbon. And where a lot of the controversy comes from is the fact that they might seem like pretty low numbers, but in this part of the world, and as we go up to Northern Australia, you only really need 0.1 to 0.6 tonnes of carbon per hectare per year to offset your beef produced on that bit of land. So obviously, if you start looking at carbon neutral and the potential to inset that emissions, it's very attractive. There's a big opportunity there if we can get the measurement right. So coming back to the whole ACCU world, it's been pretty controversial. I won't go into all those sort of things, but you've probably seen all these things in Beef Central and a lot of the arguments going on there. You know, some of these numbers that they were getting where 1 kilogram of beef sequesters 50 kilograms of CO2. So not only are you carbon neutral, you're carbon neutral 50 times over. So, you know, fantastic. But is it true? Our numbers, as per this previous slide, 0.3 to 0.7 tonnes of carbon per year in the best soils, in, you know, pretty high rainfall environment, over 20 years, averaged over 20 years. So, no, these carbon projects have been putting out. This is what they're getting paid by the government, 3 to 8 tonnes of carbon per year. So we're in this situation where, well, wait a second, the government's paying credits 10 times more than what we've seen in the science. And this is not just us, these numbers, this is global, pretty, you know, previous work by Steve Bray and his group as well. This is sort of what is realistic and expected globally, but this, and unfortunately even higher than that now in some recent credits, is really what's been credited across the industry, which has caused this friction, to say the least, between the scientists like myself and my colleagues and the industry. And don't even mention about HIR. So what's causing this? You know, why is it so difficult to measure? Well, it all comes back to the climatic variability. Here we just have rainfall. This is from a property down in Gundawindi. And we just have biomass as cents per NDVI. We have our improved grazing management and our control. So you can sort of see there is a difference between our management, but it's dwarfed by the change in just that climatic variability. So what does that mean is that when we come to do our 2 sampling points, in this case, the carbon project they went in baseline in 2016. Now, we came along, we didn't quite get that, but we measured in 2019, so right at the base of the drought. And, you know, these are soil carbon that we've gone out and we've measured independently. Lo and behold, you know, we get more rainfall, we basically see that increase into carbon. So great. So 5 years is up, carbon developer comes along, takes another bunch of soil samples, and they get a nice big carbon credit. Fantastic. Unfortunately, we have to also take this into account. We have to think about, well, you know, is that carbon going to stay there? Because getting into the system is one thing, but actually making sure it stays there is another thing. And this is where a lot of this controversy comes in, is like, well, you know, just because the carbon's there now doesn't mean it's going to stay there in the next drought, in the next dry period, after you do some sort of management change. So big opportunities, but challenging to, you know, get that confidence that we need. And so Elaine, who's now in the room somewhere, my postdoc sort of wrote a paper with this with most of the developers of that soil carbon methodology, and we basically came up with this. Well, what we really need is some reasonable bounds here. We need to put some sense behind this conversation. We need to have independent data sets that can basically give confidence to the industry about what is actually possible, so that we can still have these, you know, win-win situations, but not the controversy around it. So coming back to Turn, what the hell is Turn? Turn is, I know, the biggest network no one's ever heard of. It sells itself as Australia's Ecosystem Observatory. It's a national network. It's funded through the federal government. Hundreds of millions of dollars are going into it. It's been going for the last sort of, we'll start in 2010 when we were a founding member. But it really is this big picture national infrastructure. Now, unfortunately, they've spent a lot of time doing a lot of good work, but they haven't really been able to get across to industry. You would have used their products. You would have used some of their products. You probably used them through something like, you know, Chiba Labs or the soil mapping. You know, they're being used, but they're not being fully recognised and probably underutilised. So we're trying to bring this gap because they've got really good tools in Turn. We've got to try and bring them across. And this is where the flux towers come from. So what W2F is a flux tower? Well, first of all, they don't come from us at QUT. They come from Turn. So what is a flux tower? Well, basically, they're another way of measuring soil carbon. They're another way of measuring carbon, and carbon cycling particularly. So we can actually measure soil carbon, but we've got to measure a whole bunch of other stuff as well. But the good thing about them is that they're high resolution. You get lots and lots of data, which is great for making sure that your models that you're testing are working well. They're integrating it over big areas, and they're relatively low maintenance. So once you set them up and there's upfront costs, then they're not too bad to run. And you can sort of see they're sort of picking up an area about 500 metres. So a soil sample, you're looking at basically a core that big over 100 hectares, and you're saying that's representative. With this, we get a much more integrated number. And we pair it with soil sampling and all those other tools together, including remote sensing, to sort of bring it all together. But they're pretty robust, they're pretty reliable. This is some of our ones with our, across our existing projects with Agrimix and MLA. So this is one at Billabilla down near Gundawindi. We are also pairing it with our greenhouse gas chambers to make sure we're capturing all our sources and sinks of emissions as well. So, we don't want to be promoting things that then increase soil nitrous oxide, which, is 300 times more potent as a greenhouse gas. So we're capturing all those sort of things within our sort of standard framework. But one of the biggest benefits of this particular technology is it's not developed in Australia. Well, it's been parts of it have, but it is an international framework. So there's over $1 billion of this infrastructure globally. Like, this is not something that we came up with. This is a global international initiative where we have these things all over the world trying to answer the same question, which means it's very transferable data. It's very transferable methods to international markets. And actually our Kiwi colleagues over in the dairy world were ones that really started pioneering this in agriculture. And there's big programs in the US now as well looking at grazing management through McDonald's and those sort of things as well. So how do we use this? Well, that's a big question because we still have to tease out those climatic impacts. So going back to our paired sites, we usually have a business as usual versus an improved management, so to speak. We actually look at the data here, so this is just NEE, this is the total carbon exchange. So a positive in this case actually equals a sequestration of carbon into the plant soil system. Our yellow line in this case is actually our improved management. Our green line is our control, which is our business as usual. So in this case, you actually see over time they behave very differently. So if you're taking a sample here and you're just looking at your improved management, and you measure back here again, it's like, wow, we've got this great increase in carbon. It's fantastic. But without that paired site to actually take into account those differences in climate and how different managers interact with climate differently, we actually don't get the full picture. And actually, if we normalise that over time, where we basically just minus one from the other, we can actually say, even though in this case our improved management did lead to a rapid sequestration initially, they basically both caught up at the end. And so we've got to really, how we use these things is also very important. And so that's why we're really pushing this paired site approach. So we can basically take those things apart and really get that data that we need over a 25-year window, which is what we need for soil carbon projects, and bring it back to a couple of years so we can actually start to turbocharge some of these outcomes. And a lot of that goes into modelling. These are very, very powerful tools for calibrating models. And so what we're proposing mainly in this network is calibration validation sites that are independent, that can be used against multiple models, agnostic, but they basically bring in that data rigor that we can then use to test those models. And there's a whole range of reasons that you want to use models. You can actually predict into the future, as we've done here, running different scenarios. But they also can potentially reduce the cost of soil sampling. I mean, at the moment, going out and doing soil sampling, you're looking at $30 a hectare. The objective goal of all this stuff is to get it down to $3 a hectare. But we can do that in a way which is rigorous, and that we can basically ensure independently that the different developers that are developing their model still has that scientific rigor behind it. So introducing Altar, what we have at the moment is really following on from those existing sites. We're following them forward. We're expanding into a few different regions. We've now got some sites in HIR, but also we're teaming up with the Zero Net Emission CRC to expand that across a whole number of other sites. But the main thing is really to bridge that gap between this ecological network over this side, where they've got these really fancy tools, they're tapping into all this human resources and all this brain power internationally, and what we're trying to do in the ag space. And so we can bring it all together with these different metrics to capture a lot of these things we're talking So this is a video quickly. I don't know if that's going to play, but I've got the wrap up anyway for 2 minutes. But acoustic sensors. I'm a soil scientist, but these are one of the key things I think are going to be critical going forward. Is that video playing? Oh, okay. Because biodiversity monitoring is another one of these tools. So this all came out of Turn. This is a software package that our postdocs put together to bring all this stuff together. Now, it uses these two pieces of equipment. I can put these in the mail and I can post these out to Gregory in northern Queensland, and they can be deployed on farm by the local manager, and they can be basically automatically put into this data framework, and it's all done by AI, but it still aligns very, very strongly with the science. It still aligns very, very strongly with that scientific rigor that we need to make sure this stuff happens. And so the idea is we're trying to, remove the need to get boots on the ground for biodiversity monitoring, because these sort of tools have come so far that we don't really need to get the boots on the ground anymore. I mean, we still need calibration and validation sites. That's critical, which we'll do in the Turn stuff. But, there's an opportunity really to expand this stuff wider. And we've just released our website, so watch this space, but hoping to, really start to bring that engagement together between our two little worlds. Thank you.